And the key thing here is that we're going to use what the programmer seems to believe is correct to infer the state of the system and the rules the system has to obey. And the reason we want to do this is we don't want people to have to hold our hand to figure out what to check. So far, you've had to tell us exactly what functions return null, which functions free things, and we can't check otherwise. Okay, so just to reset very quickly. So our goal here is that we want to find as many serious bugs as we can. And when we started this, we thought that, well, you know, we're going to need really complicated analysis, or there's just not that many bugs. I mean, the code's running after all, or there's not that many rules. And it turns out that none of these things were true. Even simple analysis will actually find bugs. You know, more advanced will find more bugs, but even simple things will find bugs. There's lots of bugs, there's lots of rules. The first order problem, the main bottleneck for finding bugs is that you just have no idea what the rules are. So you look at a big system, you know, millions of lines of code, there's going to be hundreds or thousands of rules in there. You have no idea what these are. And before you can do any checking, you've got to answer questions like, you know, does A have to follow B? If it does, I can check if it does. Can foo fail? And if so, if you don't check it's for failure, it's a bug. Does var free P? If so, it's an error to use P afterwards. And does lock L protect X? And if you can answer these kind of questions, you can check and you will find bugs, guaranteed. If you can't answer them, you can't check and you'll find, of course, no bugs. And manually finding these rules is pretty hard. So it's pretty spiritually corrosive to use grep and, you know, basically play Where's Waldo with grep, trying to find answers to these questions on a couple million lines of code. We spent a lot of time doing this, you know, searching for different free, different Alex, different locks. It's really painful, and you can blow a lot of time. And you know, you have the thinking feeling the whole time you're missing stuff. And when you go to the next instance, you do it all over again. When people change the code, you have to do it all over again. So it's not really that pleasant. So instead, there's a nice trick, which is that we can infer what the code believes is correct and then just cross-check these beliefs for contradiction. And the way this works is pretty much how people have been finding errors without knowing what the truth is for at least a couple thousand years. So there's two basic approaches. One is you look for contradiction. So one way to find lies is you know what the truth is, and you ask someone questions. Anytime they tell you an answer that's not the truth, you bust them. Of course, knowing the truth is pretty expensive. So instead, you can just play cop, and you'll ask one person a lot of questions. Any answers they give you that contradict, you know, are wrong. Maybe they're lying, maybe they're not, but at the very least, they're wrong. And you can do this vertically, where you ask one person lots of questions, or you can do it horizontally, where you ask many people the same question and just cross-reference. Again, any answers that disagree, you know, are wrong, even when you know nothing about the subject or what happened or why or any of that stuff. You can immediately find errors without knowing what the truth is. This is wonderful. You can do the same thing for code. The second thing is you look for deviance. So to infer, the way this works is the more something behaves like an X, the more you believe it is an X. So for instance, the first time you sit down at a dinner table with two forks, outside fork and inside fork, and you try to figure out to start with the outside or the inside, you can look around and one guy starts with the inside fork first. You know, it could be that he's right, could be he's wrong, you're not really sure yet. If you look around the rest of the table and 100 people start with the outside fork, you're pretty sure that that was actually the right thing to do, and you're pretty sure actually that the guy who did start with the inside fork is wrong. You just do a quick probability calculation, you can bust them. And even when you know nothing about etiquette. And how we use this in code is if you see, for instance, A followed by B 1,000 times, and then you see A by itself once, this is probably an error, and you can actually calculate some probabilities. So I'll talk about how this looks like very quickly. So slightly more abstractly, we're trying to check program belief systems, where we're going to pull these belief systems out of the code and then cross-check them for contradictions. So there's two types of beliefs we have. One of these must beliefs. So these are inferred from acts that imply beliefs code must have. So for instance, if we look at this code here, if you see a star P, they must believe P is not null. If you see division by Z, you must believe Z is not 0. If you see an unlocked of L, you must believe L was blocked. And if you see X++, you must believe that L doesn't protect X. In general, if you're not trying to crash your code, anytime we see an action, we can infer you believe that preconditions hold. And so what we can do is walk over the code, ripping all the preconditions out, and then cross-checking them for correctness. For contradiction, any contradiction bug. The second type of beliefs we have are these may beliefs. So these could be real beliefs, or they could be, you could actually hardly believe it could be coincidental. So the way we do this is statistical analysis. So well, so as an example, if we see a call to A and then a call to B, it could be you believe A and B have to be paired, or it could just be that they're paired. It's harmless. It's not a big deal. It's just a coincidence. As we see A and B paired more and more, so say we see 1,000 A and B pairings, we're pretty, as each time we see an additional one, we're getting more and more sure that you really believe that they do have to be paired. It's not coincidental. And similarly, if we see a random call to B with no preceding A call, we're pretty sure that that's actually wrong. So the way we're going to check these is we just assume you really do hold that belief, and then we're going to rank errors using some probability calculations. Okay, so I'll just do one example of each fairly quickly. So first example, we're going to look at must beliefs. So this is for a straightforward security checker. In general, operating systems, this is an OS tech rule. In general, operating systems have to assume that users are bad or evil, or at least stupid. So they have rules like if a user gives you a pointer P, don't dereference it. So this is a great rule. Trivial to state, pretty easy to check. If I know this is a bad pointer, I just look up and down and make sure you don't do a dereference. And if there's one violation, unfortunately, if there's one violation, it's a pretty major security hole. A fence with one opening is not really a fence. And while we can check this with static analysis pretty easily if we know which ones are bad, if you look at a real system, it's actually really hard to figure out which are the user pointers. I spent a few days actually looking at this. So I was coming up for tenure, and my students were trying to get jobs, so we spent as much time as the main way we did both of these is we published a lot of papers. The main way we published lots of papers was find a lot of bugs, and the main way we did this was check a lot of stuff. At this point, we were trying to check this rule, burned a lot of time. In the end, you couldn't really figure out what the user pointers were because if you look in a real system, there's millions of pointers. They're cast between integers and back. They're stuffed in these weird data structures and pulled out. It's really unclear what the bad user pointers are. Now, in the end, I just gave up. But it turns out if you look at this from the point of view of belief analysis, it's really simple. Just makes the whole thing, you can just whip out a checker and you find a lot of errors. And the way you do this is you just look for two beliefs. So one is if you see a star P, that implies that the kernel believes this is a safe kernel pointer. If you see P is passed to a paranoid routine, on BSD these would be copy in or copy out. And these are routines that the kernel explicitly uses to copy memory between user and kernel space. Any pointer passed to one of these routines implies that the kernel believes it's a dangerous pointer. So you just walk over the code, and any pointer that has both beliefs, is an error. You always have to be a safe kernel pointer. You always have to be a tainted user pointer. You shouldn't be both. So we wrote this in a couple hours, ran it over the source code, and immediately out popped a whole bunch of bugs. So this is a good thing. So as a quick example, this is written as a two-pass global checker. So the first pass goes through, sees which pointers are tainted. So in this example, this is from Linux. So they pass RT to copy to user. So this means that they believe RT is a tainted pointer. So we'll mark that as a tainted pointer. Second pass goes forwards and back, seeing that tainted pointers aren't dereferenced. So in this case, what's going to happen is you get two errors because both IP, DVP, create, and delete both dereference the thing immediately. So a nice thing with this type of analysis is if you went after this bug with classical analysis, the error messages are fairly complicated. You'd have to say, well, from the system call, here's where the pointer came. The system call got stuffed in this data structure, got pulled out, went through this 20 deep call chain. Eventually, we found this bug. It's pretty hard to reason about. The nice thing about looking at belief errors is that they're very modular. So for this error, you only have to pretty much look at this box. It says, look, you passed RT to copy to user, up and delete and create, you dereferenced it. That's really all the code you have to look at. And that contradiction makes no sense. It's an error. So it's a very nice modularization of error messages. All right. So I'll give one example of made beliefs, and then we're finished. And I guess then we'll answer any detailed questions you have maybe about the product, and I can answer any detailed technical questions that are left. Okay, so made beliefs, again, these are beliefs. We're not really sure if the programmer has these beliefs or they're just coincidence. So the way we're going to do this is we're going to assume they really do have the belief, and we'll just check the code based on that. So for instance, if I don't know if you believe A and B have to be paired, I'll just assume you do believe they have to be